In this example is given a position of a particle x equal 10t square as it moves along the x-axis, where x is measured in meters and time in seconds. You are asked to find the average acceleration for the time interval from t equal 2 to 3 seconds. You are also asked to find the acceleration at an instant of time 4 seconds, and you have to answer the question, at what time is the object is at rest? To find the average acceleration for the given time interval, just write down the formula for the average acceleration, which is v final minus v initial divided by the time interval t final minus t initial. You need to find the initial and final velocity, and to do that you have to use the given equation x equal 10 equal t square by taking its derivative in order to get another equation for the velocity as a function of time. Now at this stage it is easy to find the initial and final velocities. To do that, you just substitute the time initial with 2 seconds into the latter equation in order to get an initial velocity of 40 meters per second. Likewise, for the final time, when you put it in the equation, you got an answer for the final velocity of 60 meters per second. Substitute these values into the given equation, where 60 minus 40 and divided by 3 minus 2 seconds, you're going to get 20 meters per second square. That is the acceleration of the given object. Its direction is obviously in the direction of motion, as long as it has a positive sign. To get an answer for instantaneous acceleration of this part of the problem, you need just to write down the formula for the instantaneous acceleration, which is the derivative of the velocity with respect to time. If you have an equation for the velocity as a function of time, you just take the derivative of it with respect to time, you get your answer. But if you have the position as a function of time, you need to take the second derivative in order to reach your final answer, which is a equal 20 meters per second square. Obviously this answer is independent of time. Moreover, we notice that the acceleration, instantaneous acceleration at this instant of time, is same as the average acceleration obtained earlier in part A. This means that this kind of equation is uniform equation with a constant acceleration. Finally, to get an answer for the time at which the object is at rest, you just simply substitute v equals 0 into the velocity equation. Then you get an answer of t equals 0. This is a brief picture that demonstrates the uniform motion with the constant acceleration, starting from this parabolic curve in the graph of displacement versus time, where you can get the velocity from the intersection of the line. You drop it from the time axis to intersect with the parabola, with the curve, and then you plot a tangent. At each instant of time you plot a corresponding tangent, and these tangents have different slopes, and these slopes represents the velocities. The corresponding equation to this curve is this. This is a parabolic relation, where x final minus x initial represents the displacement. Vx initial is the initial velocity, which is constant in this case, and also the acceleration ax. So the displacement is simply a function of time. By inserting any time you want to get a corresponding acceleration in it, you can get it simply by this equation. Now from the information we got, either from the equation or from the curve, we can plot a curve of velocity in meter per second versus time in seconds. This relation, as it is clearly seen, a straight line equation. And this straight line equation, we have Vx intersects the velocity axis, while the slope represents the acceleration. The equation that corresponds to this linear relation is this. This is the final velocity at any time. So you can just insert any time you want in here, this equation, and you will get an answer as long as you've got the initial velocity and the acceleration in the problem. And as you know, the slope is constant and the acceleration is constant as well. If you plot this acceleration as a function of time, obviously you will get this curve where A is constant all the way at different times. For the uniform motion with a constant acceleration, we got this equation as before, where the final velocity is a function of time and it contains the initial velocity and the acceleration in it. The second one is the displacement equals half the velocity initial plus velocity final, and all that multiplied by the time. And this equation contains most of the variables and constants and the motion except the acceleration, as you can see. The third one is the displacement again, but represented in terms of time as well, but the acceleration is available in this relation in addition to the initial velocity. And the last one is the square of the final velocities equals the square of the initial velocity plus 2 multiplying the product of acceleration and the displacement. This is a simple example that shows a truck moving with an initial velocity, and it covers a distance of 40 meters in 8.5 seconds, and it reaches up to a final velocity of 2.8 meter per second. So what is its original velocity at the starting point, and what is the acceleration? The truck here, as you see, it reached its destination after 40 meters distance and time of 8.5 seconds. Its final velocity is shown. To solve the first part of the example, where it's given that the displacement is 40 meters and the final velocity is 2.8 meter per second and the elapsed time is 8.5 seconds. With this information, you need to get this equation in order to find the initial velocity. Simply inserting all these values into this equation, you get an initial velocity of 6.6 meter per second with a direction due to the east, as the sign indicates that. It's obvious that initial and final velocity are both in the same direction. To get the acceleration in part B, with this information you need to apply this relation where the acceleration is obtained and it has a negative sign with a magnitude of 0.45 meter per second square. This result indicates that the acceleration is opposite to the initial motion. The negative sign means that this kind of acceleration is called deceleration. In this example, a toy car is found at a location of 3 centimeters with an initial velocity of 12 centimeters per second. At a later time of 2 seconds, the toy car is found at minus 5 centimeters, that is to the west. What is the acceleration of the toy car? Well, to get the acceleration of the car, let's write down the information we have. With the initial position 3 centimeters, we have an initial velocity of 12 centimeters per second, and at a later time the position was minus 5 centimeters. And then to find an acceleration, we just plot a simple diagram to represent the motion. Here delta x is to the left, to the west, and we need from this given information, we need to find the acceleration. So by applying this relation, delta x equal vx initial t plus half a t square. So we got x final and x initial, and also we have initial velocity. And just by inserting the time in this equation, you're going to get the final answer for the acceleration, that is minus 16 centimeters per second square. The minus sign indicates that the acceleration is due west, which is the same as the direction of the displacement. So the minus sign here indicates an acceleration towards the west, and in this case it is not deceleration, as long as the initial motion, as long as the acceleration and the displacement in the same direction. Well, you can check also the value of the final velocity. You can find it simply by substituting in this equation, and you're going to get a final velocity of minus 20 centimeters per second, which indicates that the car changed its direction from the east to the west, and that's why we got an acceleration in this case. Using the previous example and all the information contained in it, find the time at which the car is at rest and find its position in this moment. Now, to test your knowledge for the uniform motion with the constant acceleration, here let's answer this conceptual question. If a car is traveling eastwards, its acceleration must be varying, must be eastward only, can be eastward or westward. The answers in A and B are correct. None of the above. And the answer is C, can be eastward or west. Another conceptual question: if the velocity of a particle is zero, its acceleration can be zero, is constant but not necessarily zero, cannot be zero but is increasing with time, cannot be zero but is decreasing with time. The answers in A and B are possible. Well, the answers in A and B are possible, and that's the answer. Two cars on a race, A and B, they are in parallel lanes. At some instant of time, the velocity of car A exceeds that of B. Which of the following statements are correct? The acceleration of A is greater than that of B. The acceleration of the two cars are the same. The acceleration of car B is greater than that of A. And B is an old car while car A is a new one. None of those statements is correct. And the answer is obviously the acceleration of A is greater than that of car. Let's solve this objective question. A race car starts from rest and reaches final speed at time t. If the acceleration is constant during the elapsed time, which of the following statements are correct? The car travels a distance is the product of velocity and time. The average speed of the car is velocity divided by 2. The magnitude of the acceleration of the car is v divided by t. The velocity of the car remains constant, and none of answers A through D is true. The answer is the magnitude of the acceleration of the car is v divided by t.